Have you ever stopped to think about the simple act of drinking from a straw, or even just turning on a tap? Well, it turns out there's some incredible, kind of hidden physics powering it all. So today, we're going to dive in and uncover these invisible forces that control how liquids move all around us every single day.
Okay, let's start with something we've all done a million times. You put a straw in your drink, you take a sip, and the liquid just comes right up. But what is actually going on there? What force is making that water defy gravity and climb up into your mouth?
Now, if your first thought was suction, you're not alone. That's what most of us think. But, get ready for this, there's actually no such thing, at least not as a pulling force. The whole idea of suction is one of the biggest misconceptions in basic physics, and we're about to bust it wide open.
To really understand what's happening in that straw, we have to uncover the one fundamental secret behind how all fluids move. And I mean all of them, from the soda in your cup to the water flowing through miles of city pipes. And here it is. This is the key to everything. Fluids don't get pulled, they get pushed. And that push always comes from a difference in pressure. So if you want to move a liquid or a gas, you have to create a high-pressure spot and a low-pressure spot. The fluid will always flow from high to low. That's it. That's the engine. And check this out. It makes perfect sense when you see it laid out like this. On the left, if you have equal pressure, equal forces pushing from all sides, nothing happens. The fluid just sits there. But on the right, as soon as you create an imbalance, a stronger force on one side, boom, you get movement. That's our pressure difference in action. All right, so now that we're armed with this secret weapon, the idea of pressure difference, let's go back to our original mystery. Let's solve the riddle of the straw once and for all.
So picture this. Before you do anything, the straw is just sitting in the glass, and the water inside it is in a perfect standoff. You've got the air in the room, the atmospheric pressure, pushing down on it from the top. You've got gravity pulling the water down, and then you have the pressure from all the water around it pushing up from the bottom. It's a perfect balance. Everything's still.
But then you step in, and here's the crucial part. When you suck on the straw, what you're really doing is removing air molecules. You're clearing them out. By doing that, you've just instantly created a zone of low pressure at the top of the straw. The downward push from the air inside is now super weak. And here's the payoff. With that pressure at the top basically gone, the upward push from the bottom is now way stronger. It's totally unbalanced. And that strong upward force literally pushes the liquid up the straw and into your mouth. See? It was never being pulled up by suction. It was being pushed up by the atmosphere all along. Okay, a straw is cool. But what's really mind-blowing is that this exact same principle, this pressure difference, is what makes our entire city water systems work. It scales up in a huge way. You've probably seen water towers, right? Well, they're not just for storage. They're all about using height. Think about it. That giant, heavy column of water creates an insane amount of pressure at the bottom, just from its own weight. So at the base of that water tower, the pressure is massive. But when you open your kitchen tap, what's the pressure there? It's just the normal atmospheric pressure of your kitchen, which is tiny in comparison. And there it is again, a huge pressure difference. That's the force that pushes water through miles and miles of pipes to get to your house. Okay, so we've nailed down what makes water move, but what about how fast it moves? Like, why does water shoot out of a garden hose when you pinch the end? Well, that brings us to the second big rule of how fluids flow.
It all starts with a really simple fact. You can't really squish water. It's what we call incompressible. So that means if you shove, say, a gallon of water into one end of a pipe each second, a gallon has to come out the other end each second. The amount of water flowing has to stay the same. And of course, physics has a beautiful, simple formula for this. It's called the continuity equation. All it says is that the area of the pipe times the velocity of the water, or A times V, has to stay constant. If one of them goes up, the other one has to go down. Let's just walk through that. Imagine water just cruising along in a nice wide pipe. It's got a big area, so it can move at a relaxed speed. But then, the pipe gets narrow. The area, A, gets smaller. To keep that A times V number the same, the water has no choice. It has to speed up. And that is exactly what's happening when you put your thumb over the end of a garden hose. You are dramatically shrinking the area the water can escape from. And to keep the same amount of water coming out, it has to accelerate, turning that lazy flow into a high-speed spray. Simple as that.
So, there you have it.
The two golden rules that explain so much about the world. Rule number 1, fluids are always pushed from high pressure to low pressure. And rule number 2, if you squeeze the flow into a narrower space, it has to speed up.
Now that you've got these two principles in your back pocket, you're going to start seeing them everywhere, from how a perfume bottle sprays to how wind gets faster when it funnels between two tall buildings. So the next time you see a liquid on the move, just take a second and ask yourself, which rule is at play here? What other mysteries can you solve?